Hello and welcome to this video. In this video, we are going to look at the marking scheme of the KCSE Physics Paper 2 of the year 2015. Now, before we look at the answers to the various questions, I'd like to alert you that you can download this question paper from the video description. And in fact, I would recommend that you download the question paper, you try to do the questions first, and then you look at the marking scheme, as we are going to discuss in this video. At the same time, I'd like to remind you that if you scroll all the way to the end of that paper, you will find that I've given you links to other videos that I consider to be very useful to you at this moment when you are revising. So at the very end, you will find all these links. They're just direct links. If you click on that link, it will open that video and you'll be able to look at that particular paper. So let's go straight to the first question. Now in this first question, it is on a reflection of light. You're told that the figure shows three mirrors arranged at right angles to each other. A ray of light is incident on one of the mirrors. We are required to complete the diagram to show the path of the ray after reflection on each of the mirrors. When such a question is given, you will realize by now that we are testing the first law of reflection, which states that the angle of incidence is equal to the angle of reflection. So this is the incident ray. This is the point of incidence. And what angle is this? This is not the angle of incidence. It is the angle that the ray makes with the mirror. Let's review how we define the angle of incidence. At this point of incidence, we usually draw a line which is perpendicular to the mirror, and the angle that the incident ray makes with that line which is perpendicular to the mirror is what we refer to as the angle of incidence. So here we are going to draw a normal, and that angle will be 60 degrees. And then we use the first law of reflection, which states that the angle of incidence is equal to the angle of reflection. So that ray will be reflected like that. That reflected ray will be the incident ray as far as this other point is concerned. So you're going to see that since this will be 30 degrees at this particular point, let me just go to the next slide because I've already done it. So this is 60 degrees, this is 60 degrees. Angle of incidence equals to the angle of reflection. So this is 30, this is 90, and this is 60. And the angle of incidence at this point will be 30 degrees. So the angle of reflection will also be 30 degrees. So the ray will be reflected like this. So this again will be 60 degrees, and this will be 30 degrees. And this will be 60 degrees, and this again will be 60 degrees. So that is the way the ray is going to travel. You can go ahead and indicate the angles on the diagram. For instance, we have just said that this angle here is 60 degrees because it is the angle of incidence. This is another 60 degrees because the angle of reflection. This will be 30 degrees. Since this one is 90, then this will be 60 because angles in a triangle, the sum of the angles in a triangle will be 180 degrees. So this again will be 30 degrees because this is 90 degrees. Again, the angle of reflection here will be 30 degrees. This will be 60 degrees. When this ray strikes this point, this again will be 30 degrees because the sum of the angles in a triangle is again 180 degrees. That means that this one is 60 degrees and the angle of reflection finally here is 60 degrees. So the first thing that you should observe is that you should be able to indicate these angles on the diagram as well as give your rays arrows. You should put arrows to your rays. So ensure that that one is done. All your rays should have arrows and that these angles should be correct. And remember, the rule that I'm using is the first law of reflection, which says that the angle of incidence is equal to the angle of reflection. Remember that if you're given this as a mirror and the ray which approaches the mirror is the one which is the incident ray, the point where it strikes the mirror, we usually draw a line which makes 90 degrees with the mirror, and we call that line the normal. Remember, it is not a ray. So this angle here is what we call the angle of incidence. Many times the examiner gives us this angle here, and the students end up thinking that this is the angle of incidence. It is not. The angle of incidence is the angle between the incident ray and the normal. And then this ray is going to undergo reflection. And that is where now we realize that this angle here is the angle of reflection. The angle between the reflected ray and the normal is the angle of reflection. And again, we use this law here. So remember, when you are drawing a ray diagram, always give your rays arrows, and then remember to identify the angle of incidence and the angle of reflection, and then use this law here. That is where the 3 marks go. Let's look at question number 2. Now in question number 2, we are told that it is observed that when a charged body is brought near the cap of a positively charged electroscope, the divergence of the leaf increases. State the type of charge on the body. So this is a leaf electroscope, and we are told that it is positively charged. When we say that a body is carrying a certain amount of charge, for example, this one carries a positive charge, it does not mean that the other charged particles don't exist. The particle which is responsible for making the body to be positively charged is the proton. What it means is that this electroscope has got more protons than electrons. That is why it is positively charged. Remember, a neutral body has the number of protons being equal to the number of electrons. That is what a neutral body is. If that neutral body loses electrons, then the number of protons, of course, become more than the number of protons become more than the number of electrons, because it has lost some electrons. That is what a positively charged body is. So how does a neutral body become negatively charged? A neutral body becomes negatively charged if it gains electrons. So bodies become charged by the process of electron transfer. Now in this question, we are told that a positively charged body, or rather a charged body, is brought near the cap of a positively charged electroscope. We do not know the charge on this body, but we observe that the divergence is going to increase. When that happens, it means that the magnitude of the positive charge is increasing at the leaf and this rod here. How does that happen? It means that more electrons have migrated upwards, and wherever they come from, they leave unpaired protons. That is what happens. The only thing that can make these electrons to migrate upwards is because the new body must be attracting more of these, more of the electrons. So the new body must be carrying a positive charge. On the other hand, if we observed that there was a fall, it would indicate that electrons are migrating downwards, neutralizing some of the positive charge here, and that is why there is a less repulsion, leading to the leaf falling. So what can make these electrons to migrate downwards? Either we can have a body which is just a conductor, which is just a conductor. If it is just a conductor, it means that electrons on this conductor, remember it is not charged, electrons on this conductor are going to be attracted by this positive charge, and they are going to put themselves close to this end of the conductor. So electrons are going to rearrange themselves in this body such that electrons will migrate this way, leaving the positive charges on the other side of this conductor. This negative charge here is going to repel electrons from here, and that is why they move downwards. That's why they move downwards, causing a decrease here. The other possibility is that if we have a negatively charged body, we bring it to this cup here, it will have the same effect as having a conductor which is not charged. So at that point, we would not be sure whether the body we have brought here is carrying a charge or it is just neutral. So here it is carrying a negative charge, but here it is not, it is neutral. It is not possible to identify the type of charge on the body because there are two possibilities. Either that body could be a conductor which is neutral, or it could be a body which is negatively charged. And that is why repulsion becomes the only sure test of the charge on this body. So the moment we see that there is leaf divergence, then we conclude that there must be repulsion between the positive charge on the charged body and the positive charge on the electroscope, leading to that kind of repulsion. So over here, we would just expect to see that the type of charge on the body is positive because like charges repel, and the repulsion is the only sure test of charge on a body. I'm taking time to give you more information on that particular concept because you'll find that it may be tested in another paper. So let's go to question 3. State the reason for topping up a lead acid accumulator with distilled water. You see, water in the acid could evaporate, and we would top up or add more distilled water into it, and this does not change the concentration of the acid, because it is important that the concentration of the acid be kept uniform or constant. The only situation in which we would add acid is when there is a spillage. But in this case, we've not been told whether there is a spillage or not. So wherever you see that the level of the lead acid accumulator acid has dropped below a certain mark, then the best thing to do is to add distilled water. We don't add acid unless there is a spillage, because adding the acid would change the concentration of the acid. Question 4. Figure 2 shows a soft iron bar AB placed in a coil near a freely suspended magnet. Explain the observation made when the switch is closed. So let's see what happens here. So when this switch is closed, this is the positive side of the battery, this is the negative side. So current is going to flow in that direction, the direction of the arrow. When it comes here, the direction of the arrow in the coil or current in the coil would appear as shown, and we can use the right hand grip rule to identify this to be the north pole. So a north pole will be created at this point, and that is why there is a repulsion between the north pole, which is created at end B of the electromagnet, and the north pole of the suspended magnet. So this magnet, this pole will be pushed away, so repulsion is going to take place. Practically, this bar magnet is going to turn about this string. It is going to twist so that it is this other pole here which will come and face this, and immediately we'll see attraction. But we've been asked to state the immediate observation here. There is a repulsion, or this pole of the suspended magnet is pushed away, again confirming that repulsion is the only sure test of poles, just like in charges. For example, if there was attraction between a material that is suspended here, there can only be two possibilities. Either that material is a magnet, with this one being a south pole because there is a attraction, or that material is just a magnetic material. So there are two possibilities if there is attraction. Magnetic material will be attracted by any pole of a magnet, whether it is a permanent magnet or an electromagnet. And there will also be attraction between unlike poles. So in a case where we are trying to test for polarity of a certain magnet, or to identify whether the material is a magnet or not, we cannot use attraction, because if we use attraction can also occur between a magnetic material and any magnet. So repulsion is the only sure test of polarity. So again, we expect the pole on the suspended magnet will be pushed away or repelled. A north pole is induced at end B of the suspended soft iron bar. And of course, I've already explained it's because like poles repel. Let's look at question number 5. State the reason why a convex mirror is preferred over a plane mirror for use as a driving mirror. You find that when you are using a plane mirror, for example, let's assume that this is the size of the plane mirror. Let's suppose that this is the size of the plane mirror, and this is the eye of the driver. This is the eye of the driver. Let's look at his angle of view. We draw rays all the way to the edge like that, and we find that due to reflection, these rays must have been coming from this side and this side, and they are reflected by the mirror that way and that way. The angle of view of this plane mirror is this much here. This is the angle of view. So the driver cannot see anything which is outside this angle of view. Anything which is here, the driver cannot be able to see. Now let's look at the convex mirror of the same length. From here to here, from here to here, it is the same. And the distance of the driver's eye from the mirror is the same, just like before. You'll be able to see that this ray that reaches the driver, this ray here, must have come from some point here. I'm trying not to exaggerate it too much, because already what I've drawn is a highly curved convex mirror there. Let's look at the angle of view of this convex mirror. You can see that it's very big. This angle here compared to this angle here, this one is bigger. So we say a convex mirror gives the driver a larger angle of view, allowing the driver to see more details behind the vehicle that he or she is driving. So a convex mirror has a larger angle of view, allowing the driver to see more images of the object behind. Let's look at question 6. State ways in which the strength of an electromagnet can be increased. Now this question is quite direct. I just want you to be careful with the number of turns. The first property is that we can increase the amount of current flowing through the coil of the electromagnet. Usually make your answers to be as complete as possible. And over here, when we talk about amount of current, although you can be given a mark by saying increase the voltage of the battery, because it ends up increasing the current, but when you say increase the voltage, it could have other effects in addition to increasing the current. So go direct to the amount of current flowing through the electromagnet. When you come to the increasing the number of turns of the coil of the electromagnet, be very careful. Although the question looks easy, students are usually trapped here. Many students talk about number of coils. It's not the number of coils. There is a single coil with many turns. So it is the number of turns in the coil that is increased. Let's go to question number 7. State two differences between electromagnetic waves and mechanical waves. Again, this question is a bit general in the sense that electromagnetic waves, all of them have a speed of 3 by 10 raised to power 8 meters per second. But mechanical waves have varying speeds, but all of them are less than 3 by 10 raised to power 8 meters per second. Electromagnetic waves do not necessarily require a material medium in order to be propagated. Now, what does this mean? Take, for example, light. Light can travel through vacuum where there is no material medium. It can also travel through water or even glass, and these are material media. So you can see it can travel in a material medium. It can also travel in a vacuum. But when it comes to mechanical waves, they definitely require the material medium through which they move, because they travel in that medium by making use of the particles of that medium. So there is no way you can have sound waves traveling through vacuum, because there are no particles which are going to produce compressions and rarefactions. Now, the other difference is that all electromagnetic waves are transverse in nature, but mechanical waves could either be transverse or longitudinal. So those are some of the differences. I've given you 3 differences, although the examiner just wanted 2. Now, why am I giving you more than 2? I'm giving you more than 2 so that you can make your revision as comprehensive as possible. But when you are giving answers in an exam, be careful. If they asked for 2 differences, just give 2 differences. Don't be generous. Don't give more than 2. Because if you give more than 2 and the third one happens to be wrong, that wrong one will go and subtract the answer for the correct one. For example, let me just explain this using this example. Let's suppose the examiner gives you 1 mark for stating this difference. And when you're comparing 2 things, remember you say something for this one and you say something for this one. Don't allow the examiner to fill in gaps for you. So the second point is also correct. So you're earning marks here. Let us just assume that this one is not necessarily correct. Let me just assume that it is wrong. Or you write down something here which is wrong. What will happen is that since you had earned the 2 marks, this wrong one will go and subtract this. So instead of getting 2, you'll just get 1, because you've stated a factor which negates the factors that you have already talked about here. You know, the examiner interprets this to mean that you are not sure of one of them, or even the factors that you've stated here. So you are stating a third one, hoping that the examiner is going to choose the correct one. Examiners are not supposed, or markers are not supposed to choose the answers that you give. They are just supposed to test whether you understand a particular concept. So you either know it or you don't. So I hope that point about giving more than required is clear. So do not be generous. Question number 8. Figure 3 shows us straight waves incident on a diverging lens placed in a repo tank to reduce its depth. Complete the diagram to show the waves in both the shallow region and beyond the lens. So this is of course the deep part of the medium, deep part, and then this is the shallow. I forgot to name this. This is the shallow. Okay, now this is the wavelength, this distance here. It is the wavelength. When water waves move from deep, medium into shallow waters, what happens is that the speed is reduced. And because the frequency of the waves is not affected by a change in medium, what happens is that the wavelength is going to be reduced. So remember that. So you're going to proceed with this wavelength here. Let's call it A. This middle section we call it B, and this one we call it C. You're going to proceed with it until it comes and makes contact with this boundary here. So A and part C hit the boundary simultaneously. B is still on its way to the boundary between deep and shallow. So this is what is going to happen. By the time B travels this much distance all the way to the barrier, A will have entered the shallow medium and its speed will be reduced. So it won't travel through the same amount of distance. Okay, it will cover just a small distance. So it is this that I'm looking for, this short distance here, and also C covers this short distance. And now I join these 3 points, this one, and this one with a curve. I draw a curve like that. So after that, after I have obtained that curve, I remember that the wavelength is going to be reduced. So I draw the next wavefront here, the next wavefront here, the next one here. Okay, by the time this reaches here, let's assume that maybe this wavefront just reaches this point, okay? You'll find that B this time is the first one to move into the deep region. By the time A is somewhere around here, because it has to continue with the same wavelength, so by the time C is here, you will find that B would have covered a bigger distance into the deep medium. So you're going to join this point and that one there, so that by the time the whole of it has reached, reaches that point, this is what we are going to have. We are going to have the waves, they would have recovered their original, of course this point is supposed to have met somewhere around there. The original wavelength of the waves has been recovered. And now you can continue by drawing the other wave fronts. So I've already drawn this one accurately for you, and here it is, and I've explained everything. One other thing, this point here does not undergo any change in direction, but this point here will bend towards the normal, and that is why there is this aspect there, like that. Another thing to observe is that this curve here is not parallel to the boundary here. This is a mistake that many students make. You see this curvature of the boundary and the curvature of my wavefronts, they are different, and I've already explained how that one comes about. But even in textbooks you find that they make that kind of mistake. So it's good if you try to be as accurate as possible. Just follow the points that I've explained here. Let's look at question 9. A ship in an ocean sends out an ultrasound whose echo is received after 3 seconds. If the wavelength of the ultrasound in water is 7.5 centimeters and the frequency of the transmitter is 20 kilohertz, determine the depth of the ocean. This concept is the one of like clap echo method. If you have this one as the boat or the ship, and this is the surface of the ocean like that, and a signal is produced from there. It goes all the way, strikes the bottom of the ocean, and then it is reflected back and it is received by a receiver there. So there is the incident wave, this is the reflected one, this is a transmitter, this is the receiver, and the time for the waves to cover a distance d plus another distance d, in fact 2d, is recorded. So if I were to calculate the speed of these waves, I would do something like this. I would say speed is equals to the distance covered, which is d plus another d, d plus another d. We are going to assume that this distance here is the same as this one here, because when we compare the width of the ship with the depth, you find that it's almost negligible. This angle is almost like 90 degrees. So it's as if the transmitter is here and the receiver is at the same point. So let's go on. Divide by the time taken to move d plus another d. In other words, v is equals to 2d over t. You have used this equation before, but in most cases we usually give you this speed here. But in this question, what we have given you is the wavelength of the waves and the frequency. So this is 20 kilohertz is like 20,000 hertz. So you will combine this wavelength and the frequency to get the speed, because speed is frequency times wavelength. But the same speed is 2d over t. So you can substitute everything here in order to calculate the depth of the ocean. Again, I've already done that one for you, and this is it. So we use 20,000, and that distance there must be in centimeters. So I divide by 100 to get it into meters, and I get 1500 meters per second. And then I use v is equals to 2d over t to get the depth of the ocean to be 2,250 meters. Question 10. We are given a nail at the bottom of a beaker containing glycerin appears to be 6.8 centimeters below the surface of glycerin. What does this mean? This is what it means, that there is this container of glycerin here. This is the bottom of the, or rather, something like that. There is some glycerin here. Then we've got an object at the bottom here, which is a nail, this nail, and it appears to be 6.8 centimeters below the surface. So we know that the nail appears to be somewhere here. So this is its apparent depth. This is its apparent depth. Its actual depth is actually this one. Now, since we've been given the refractive index of glycerin as this, the equation to use here will be real depth over the apparent depth should give us refractive index. And again, I've already done it for you here. Refractive index of glycerin is real depth over the apparent depth. 1.47 real depth is what we are looking for, and the apparent depth is 6.8 centimeters, in which case we get 9.996 centimeters. Let's look at question 11. In question 11, we want to state one application of thermionic emission. One of these would be in the cathode ray tubes, or CRTs, which finds application in TVs and the CRO, but modern television sets no longer use this idea of the thermionic emission. They use a different technology altogether, but initially TVs were using this. CROs are still using this technology. Radar systems also were using that technology at some point. But here, it's just an application that is required. Let's go to question 12. Figure 4 shows cathode ray entering into a region. Cathode rays are fast-moving electrons. They enter into a region between two charged plates. The upper plate is positively charged, the lower plate is negatively charged. So there is an electric field here complete the diagram to show the path of the ray in the field. It's important that you show that, okay, these electrons would have followed this path if the electric field is switched off, or if it was not there. But as soon as they reach this particular point, this is where they are affected by the electric field. And because they are electrons, they will be attracted to the positive side of this plate. So they will experience a force here due to the electric field in that direction. So they're going to curve out like that. Curve out. So the path is parabolic, because the path is always, the force is always like this. It is at the initial point where it is perpendicular to the direction of travel. But as time goes by, it's no longer perpendicular to the direction of travel. So the path becomes what we refer to as part of a parabola. So it is parabolic. But as soon as it leaves the electric field, you should be very careful to observe that it travels in a straight line. In the absence of electric or magnetic fields, these charged particles usually move in straight lines. It's one of the properties of cathode rays. They move in straight lines. So here we don't have any electric field, so it moves in a straight line. But over here, of course, it curves. So marks would be given for showing this kind of curve and then a straight line, just in case you want to complete or to show beyond that point. I'm usually disappointed by students who usually continue this and they continue carving it out like this. But this one does not happen, okay? Just reach this point, stop at that point, and then from there, draw a straight line. Let's look at question, and of course, I've already done it for you over here. So let's look at question 13. When a transformer is connected to an AC source, the output voltage is found to be 24 volts. So this is the voltage of the secondary. So here we can say Vs is 24 volts. Of course, it is AC. If the power input is 2000 watts, power input, 200 watts, determine the output current. Assume the transformer is 100% efficient. A transformer which is 100% efficient means that the input power is always equal to output power. Input power is 200 watts. Output power will be the current times the voltage. Of course, this one is also the current times the voltage, but I do not want to bother myself with current in the primary times voltage in the primary, because I've already been given the product of these and these. It is on the right hand side where I'm required to calculate the current in the output or the current in the secondary. And using this expression, I'm able to get the correct answer. So 200 is equals to 24 times current in the secondary. I get 8.33. Question number 14. 14 part A. State two factors that affect photoelectric emission. There is the energy of the incident radiation and the intensity of the radiation, as well as the type of metal that is used as a target metal. B. Light of wavelength 4.3 by 10 raised to minus 7 meters is incident on two different metal surfaces, nickel and potassium. Take speed of light to be 3.0 by 10 raised to power 8 and Planck's constant as 6.63 by 10 raised to minus 34 joules seconds. Determine the energy of the incident radiation. This is very easy. Energy of the incident radiation is equal to Planck's constant times the frequency of that radiation, and of course frequency is the speed of a wavelength, so I can substitute for frequency as speed of a wavelength. In photoelectric effect or in quantum physics, we usually use C to be the symbol for speed of light, C. But even if you were to use V, it is understood. So when I substitute all these values inside here, I get 4.625 by 10 raised to minus 19 joules. 4.625. Let's look at part B. In part B, we are asked to determine the energy of the incident radiation. We have already determined that, and we have got it to be 4.25 by 10 raised to power minus 19 joules. Okay. Now, if the work function of nickel is 8.0 by 10 raised to power minus 19, notice that the power is the same as over here. That one is important because we can make a comparison between this and this. And potassium is 3.68 by 10 minus 19. Again, we can make a comparison between this and this. State with a reason from which of the two metals the given light will eject electrons. If the work function of nickel and potassium are as given, state with a reason from which of the two metals the given light will eject electrons. Now, potassium will be the metal from which electrons are going to be emitted. It's not possible to emit electrons from nickel because its work function is far much greater than the energy of the incident radiation. So, potassium from a metal with a work function lower than the energy of the incident radiation. Here I give some extra information. The electron that is being removed absorbs all the energy of the incident radiation as a complete packet and not in bits. It then allocates the energy to its own work function and uses the rest of its own as its own kinetic energy. Therefore, it never absorbs this energy in bits. So that energy of the incident photon, first of all, it must be greater than the work function of the metal. Therefore, the energy absorbed must be at least equal to the work function for photoelectric effect to take place. And we have just seen that that is one of the conditions for photoelectric effect to take place. Now let's go on. Determine the velocity of the emitted electrons from the metal surface in B part 1. Take the mass of the electron as 9.1 by 10 raised to minus 31 kilograms. Again, this one is calculated using the Einstein's equation of photoelectric effect. In other words, the energy of the incident photon is going to be equal to the work function of the metal plus the kinetic energy of the emitted electron. So you can be able to see that when I substitute in these values, I'm able to get the kinetic energy of the emitted electrons. But I already know that kinetic energy is a half mv squared, a half mv squared. So I know the kinetic energy, I know the mass of the particle. Of course, a half is just a number. I can be able to calculate the speed of these electrons, which is 4.56 by 10 raised to power 5 meters per second. Question 15. State two factors that affect the resistance of a metallic conductor. Of course, this is the length of the conductor, the cross-section area of the conductor, and the material from which the conductor is made. We get this from this equation here. Resistance is equals to resistivity, which is about the material, length, and area. These are the factors, but we were not asked to state how each one of them affects the resistance. If that one was given, we would have said resistance is directly proportional to the length, it is inversely proportional to the cross-section area, and resistance of a given material is proportional to the resistivity of the material. B. Explain how a fuse safeguards electrical appliances against excessive current. We want to start by stating here that a fuse has a rating. What is meant by that? The current above which it will melt and open the circuit is called its rating. So how do we choose fuses? A fuse is chosen in such a way that its current rating is just above the current which will destroy the appliance, so that it opens the circuit when this current is reached. So I hope this explanation is quite clear. Let's look at how it is applied in problem solving. In part C, we are given that a hairdryer is rated 25 kilowatts, 240 volts. At this point, I take time to remind you that the power rating of an electrical appliance means that you must be given the power and you must be given the voltage to which it must be connected for it to deliver this power. Because if this voltage is less than this value, then it will not deliver this power. So in rating of electrical appliances, the power and the voltage must be stated. Okay, determine whether a 10 ampere fuse may be suitable for the hair dryer. We want to calculate the current which must flow through it when it is working normally, and the equation to use is P is equals to IV. P is equals to IV, meaning that I is equals to P over V, and that is what I've used here, and I get 10.4 amperes. So the best fuse rating is 11 amperes. But here we can see that if we try to use a 10 ampere fuse, this fuse is going to blow even when the appliance is working normally. So it will not allow this appliance to work at all. The fuse will keep on blowing even if the current is just the correct one. So a 10 ampere fuse is not suitable because it will blow even when the appliance is working normally. Part 2. Determine the cost of using the hair dryer for 2 hours if the cost of electricity is Kenya shillings 80 cents per kilowatt hour. When you're given this type of question, I usually recommend that students remember this equation here. The cost is given by the number of kilowatt hours times the rating. In other words, you calculate the energy consumed in kilowatt hours. You can see this is power in kilowatts and this is time in watts. So when we multiply power by time, we usually get energy. So get the energy consumed by converting the power in the appliance to kilowatts. That is the first thing. If it's not already converted, then you've got to convert it into kilowatts. Then convert the time that it is in use into hours. And then multiply by the rating which is given by the company. And when you do that, you're going to get actually a cost for using it for 2 hours will be 4 shillings. Question 16. It is observed that alpha particles have a lower penetrating power than beta particles. Explain this observation. This can only be explained by using the fact that alpha particles have got a very large mass compared to beta particles. They therefore are likely to collide more with atoms of other substances of the material through which they are trying to penetrate, for example, air molecules. Therefore, alpha particles are stopped because of their big mass, while the mass of the beta particles, which is an electron, is very small. Part B. A radioactive substance has a half-life of 12 years. Determine the time it would take to decay to 12.5% of its original value. Let's see, 12.5% of its original value is like a quarter. So this is how we do it. We get the original substance, which is like this, when time is 0. After a time equal to 1 half-life, a half of that will decay. So we're going to divide it into 2. This is the one that has decayed. This is the one which is remaining. So if it was 1, so a half will be remaining. Or if it was 100 or even 100%, 50% will be remaining. After another time equal to another half-life, a half of what was remaining Let me just draw this as it was there. A half of what was remaining. So I divide this one into 2. In order to divide 50% by 2, I get 25%, will decay. And then after another half-life, T half, a half of this. So I'm going to first of all draw it as it is here. So a half of this will decay. So what is remaining is a half of this, which is, I divide this one by 2, I get 12.5%. And this is how I get a total of 3 half-lives. This one, and this one. So the time that has elapsed is 36 years. Question number 16. A Geiger-Miller tube is used to detect radiations from a radioactive source. State the function of the small mica window. The mica window is made thin enough to allow radiation to enter into the GM tube. Again, you realize that there is need to keep the air pressure in the GM tube to be as low as possible, so that the radiations, especially those of alpha particles, are not stopped by air. So we try to reduce the pressure inside the GM tube to be as low as possible. So we must put a window which is covered by this material. So that material is made to be very thin so that even alpha particles can be able to penetrate. Now, why is bromine gas used in the tube? Now, when radiation enters into the GM tube, it ionizes the argon gas which is inside there. It ionizes the argon gas. I think this one is something that is missing. I may not have captured it very well, but let me just explain this by saying that it ionizes the argon gas inside, producing a negative and positive producing ions. Now, if these ions were to collide with the cathode, positively charged ions will move towards the negatively charged part of the GM tube. If they were to collide with the cathode, electrons would be produced, which would cause a second electron avalanche, resulting in a false pulse. So there is need to prevent these electrons from being produced. There is need to prevent these positively charged ions from making contact with the cathode. And that is why we use bromine gas. It acts as a stop. It prevents the positively charged ions from making contact with the cathode and thus act as a quencher. It is a quenching agent. D part 1. In a diffusion chamber, explain how some of the tracks formed are observed to be short. Of course, the track is short, showing that the range in air is small. That is why it is short. Particles whose range in air is smallest are those of alpha particles. So the diffusion chamber allows you to identify the type of radiation which has come into it, or which is being investigated, or which has produced those tracks. The path of the particles cannot be changed by collision. Okay, the reason why they are straight, it means they've got very high momentum, and therefore their path cannot be easily changed even with collision with air molecules. The only particles which possess this property, that they've got high momentum, are alpha particles. Again, these particles, the diffusion chamber is used to identify the type of particles which come in. Next, in D part 2, we are asked to state 2 advantages of using a GM tube instead of a diffusion chamber to detect radiation from a radioactive substance. Of course, a diffusion chamber is rather bulky and it cannot be used within it's not portable, and of course there is no need to charge it as it happens with the cloud chamber, because for the cloud chamber to work, there is a part which must be charged by rubbing the glass with a material so that those tracks can condense around the charged particles. So this one requires some further preparation before it can be used, but the GM tube, all you need to do is just connect it to electricity and it's ready to be used. So it therefore does not need much preparation, that is the GM tube, before use. The diffusion chamber, on the other hand, has the advantage of being able to detect the nature of the radiation or the type of the radiation, which can be determined or identified from the type of tracks that are produced. Let's look at question 17. State 3 factors that affect the capacitance of a parallel plate capacitor. This one is quite direct. One of them is the area of overlap between the plates. The second one is the distance between the plates or the separation. And the third one is the value of the dielectric constant between the plates. Part 2 or B of 17. Figure 5 shows the circuit used to charge a capacitor C. So this is a capacitor. State what would be observed on the following when the switch is closed, the milliammeter. Current will initially shoot instantly to a maximum value and then decrease to 0 when the capacitor is fully charged. How about if it was a voltmeter? Actually, the answer here should be the voltmeter reading increases from 0 to a maximum value. This part here is not there. This part is not there. So the voltmeter reading increases from 0 to a maximum value when the capacitor is fully charged. So just cancel out this 0. It is not meant to be there. So the sentence should read, the voltmeter reading increases from 0 to a maximum value when the capacitor is fully charged. Part 2 of B, explain how the capacitor gets charged. Of course, I've given a detailed explanation here. It's quite obvious that this plate here is connected to the positive side of the battery. What the battery does is that it removes electrons from this plate, and the same battery deposits the same electrons onto the other plate. So when a neutral body, in this case this plate, loses electrons, it becomes positively charged. So this plate will carry a positive charge. Again, when a neutral body acquires charges from elsewhere or receives electrons, it becomes negatively charged. So the plate connected to the negative terminal of the battery becomes negatively charged. So that is how it happens. So let me quickly read these sentences that I've written here. The battery removes electrons from the plate connected to the positive terminal of the battery and deposits them onto the plate connected to the negative terminal of the battery. The plate which loses electrons becomes positively charged, while the plate which gains electrons becomes negatively charged. So this is what you will find out. Now let's say this plate here will acquire a positive charge of 1 microcoulomb. This other one will acquire a negative plate of negative 1 microcoulomb. When you connect, when you are considering the object in totality, the capacitor as a whole, you will find that the positive charge is equal in magnitude to the negative charge. So when you combine them together, you will find that the capacitor is neutral. So although we talk about a capacitor getting charged, it does not mean that it's going to have a certain net charge. All it means is that electrons have been, the charges have been separated. Electrons have moved from one plate to the next or to the other. So if we have 5 electrons on this plate, it left 5 positives on the other plate. Once you separate the charges like this, what is stored in the capacitor is energy. Energy is what is stored in the capacitor. But when it comes to charge, a charged capacitor is neutral, so to speak. Let's look at the purpose of the resistor R. This resistor serves the purpose of slowing down the charging process so that we are able to read the current and the voltage as the charging process continues. So, resistance usually increases or reduces current in a circuit, and current is the rate of flow of charge. So the rate of flow of charge is reduced when the resistance is high. That allows us to detect this current, how it is changing with the time, so that you can be able to plot various graphs. The voltage similarly can be detected. When it comes to discharging the capacitor, it also discharges across the same resistor, and again the current and the voltage can be detected during the discharge process. Practically, when you get this capacitor and connect it to any DC circuit, it just gets charged instantly without any time lapse. So that does not allow us to observe the ammeter and the voltmeter. Now when it comes to part B, we have been asked that figure 5 shows the circuit used to charge a capacitor. On the axis provided, sketch the graph of voltage against the time for the charging process. So the voltage is going to increase until it flattens out when the capacitor is fully charged, like that. So the voltage increases like that and then becomes constant. When it becomes constant, we are sure the capacitor is fully charged. Question number 18. 3 resistors of resistances 2 ohms, 3 ohms and 4 ohms are connected to a cell such that they have the least effective resistance. The point to note here is this: effective resistance means total resistance, and that total resistance has got to be the least. So it follows that these resistors must be connected in parallel so that the total resistance will be smaller than the smallest resistance here. That one's a point that you should be able to understand. 2 ohms, 3 ohms, 4 ohms. The total resistance will be less than the smallest resistor which has been used. This is always a fact, and we are going to see when we do that. So the circuit will be like this. All of them must be connected in parallel. When it comes to calculate the total resistance, of course we must do 1 over R. This is the effective resistance, is equals to 1 over R1 plus 1 over R2 plus 1 over R3. We find the LCM and then we invert this. I want to point out something which makes many students to lose marks. They start something like this, which is wrong. They say RT is equals to 1 over 2 plus 1 over 3 plus, and they continue like that. Already here there is a mistake, and the mistake is here. So remember, it is not RT that you're working out here, it is 1 over RT, so that eventually you'll have to get the inverse of it. So be careful with such small parts. In part B, we are told that question 18b, a real object of height 1 centimeter placed 50 millimeters from a converging lens forms a virtual image 100 millimeters from the lens. Determine the focal length. Of course, here it's just a matter of identifying V. Why did I give it a negative sign? It's because the image is virtual. The image is virtual. That is why. It is 100 millimeters from the lens, so this is my value of U. When I use this equation in consideration with the negative sign over there, I get F to be 100 millimeters. And of course, the magnification is V over U, which is 2. The last part is where I'm asked, on the grid provided, draw to scale the ray diagram for the setup. to show how the image is formed. Of course, I've tried to do that on this diagram. Just pause the video, study it carefully, and one of the things I'd like you to note is the direction of the arrows. I've not forgotten the arrows. That one is so important. So important. So that is all that I had for you in this particular paper. I want to thank you for being with me in that process. Go to the video description, download the question paper, and remember to go to the links at the end of that paper where I've given you more videos which are going to be of use to you as you revise for your forthcoming examination. Bye-bye.